Hello everybody! In this video, we're going to learn about quadratic forms and conic sections. Now, this is a topic you might have seen in a high school algebra class. Conic sections are different shapes you can graph in a plane. So for example, circles or ellipses or hyperbolas. And since it's been a while, we'll do a little review of these topics first. And then we'll talk about something called a quadratic form. That's a special kind of a function involving a matrix. So our goal in this video is going to be to use what we've learned in matrix algebra to graph equations, quadratic-like equations that look like this. Ax squared plus bxy plus cy squared equals 1. It might kind of remind you of a parabola with that x squared term in there, but the presence of the y squared term indicates it might be more like a circle. But then we have this bxy term, which makes things a little bit interesting, as we'll see. But before we get ahead of ourselves, let's review graphing quadratic equations that look like this. Ax squared plus by squared equals 1. So in this case, there's no xy term. Well, there's a few common cases we might look at first. For example, what if both the coefficients a and b here were both equal to 1? Well, in that case, you'd be left with the equation x squared plus y squared equals 1. And that's the equation of the unit circle. That's the circle centered at the origin with radius 1. A very common equation you see in mathematics. Now there are some other cases as well. What if a and b are both positive numbers? In that case, in general, you'll get the equation of an ellipse. It kind of looks like a slightly flattened or squashed circle. And in the special case where a and b are both the same, that will cause this to actually be a circle of some radius. But in general, we'll more commonly encounter ellipses. Now, what if there's a negative sign in this equation? In other words, what if the coefficient a is positive while b is negative? Or, what about the opposite case, when a is negative and b is positive? In either case, if you have opposite signs here, there's going to be a subtraction involved, and the shape you get is a hyperbola. The hyperbola looks like two disconnected curved segments, kind of like two symmetric parabolas, but not quite. So these are the two kinds of shapes you could get depending on your case. And what if a and b are both negative for the sake of completeness? Well, if they're both negative, then this equation actually cannot have a solution. If a and b are both negative, x squared and y squared are both positive, when you combine them, you'd get a negative number on the left and a positive number on the right, and that's not possible. Now, let's look more in depth as to how you would graph ellipses and hyperbolas, the two most common situations we're going to encounter. So first, let's take the case of an ellipse. To begin, we'd like to rewrite this equation, ax squared plus by squared equals 1, in this format. X squared divided by alpha squared plus y squared divided by beta squared equals 1. And so it's kind of like we want to turn these into fractions and figure out what number goes in the denominator. And to do that, it's kind of a substitution. And so here, the coefficient of x squared is a. Here you can think of the coefficient of x squared as 1 over alpha squared. And if you set those equal to each other, a equals 1 over alpha squared, you can do some algebra and rearrange, and you'll get alpha is equal to 1 over the square root of a. Similarly, b can be set equal to 1 over beta squared, and beta is equal to 1 over the square root of b. And since both a and b are positive, we have nothing to worry about in terms of imaginary numbers. Now, the reason we'd want to rewrite this equation in this form is it becomes easy to identify 4 points which will be on this graph. So in particular, this graph, the graph of the equation in this form, will contain the points plus or minus alpha, comma 0. So it contains this point and this point. Why do we know the graph contains these points? Well, what happens if we plug these numbers back in for x and y? If we plug either positive or negative alpha in for x, the squaring would cancel out the negative sign if there was one, and this fraction becomes 1. Plugging in 0 for y turns this fraction into 0, and 1 plus 0 is equal to 1. So that shows us why that point is on this equation. Similarly, the points 0, comma, plus or minus beta are also on this graph. And again, you can figure that out, you can verify it, by plugging these values in for x and y, and you'll also end up with the equation 1 equals 1, validating that these points are also on the graph. And then this just gives you a way to kind of roughly trace out the graph, and it looks curved and it goes through these 4 points. In fact, you can kind of think of alpha and beta almost as radii of this curve. A circle really only has 1 radius, an ellipse kind of has 2. And sometimes these are also called the major and minor axes of the ellipse. But those words won't really be important. The important thing is identify some points on your curve and draw a rough sketch of what the ellipse would look like. As a more concrete numeric example, let's say you want to graph the quadratic equation 5x squared plus 1/4 y squared is equal to 1. Well, 5x squared you could rewrite as x squared divided by 1 over square root 5, quantity squared, plus 1/4 y squared, and that's already in the form of a fraction for us. So that 4 in the denominator becomes a 2 squared. And that's equal to 1. So we know we have an ellipse, right? Along the x-axis, 1 over the square root of 5, that's about 0.4, slightly less than a half. And here, well, this number is 2, so kind of the axis along the x direction, that's 0.4. The axis along the y direction, that's 2. And then just kind of connect those points like so. And that's more or less what that ellipse will look like. It's not perfectly to scale, but it's not an art class, so this will be close enough for our purposes. Hyperbola is a little bit more confusing, but still totally doable. So to begin, we'll take this equation, and this will be the case where b is negative, so I'll just write that as minus a positive value. But we'll rewrite this equation, ax squared minus by squared equals 1, rewrite it in the same form, x squared over alpha squared minus y squared over beta squared is equal to 1. And again, you can solve for alpha and beta in the same way that we do for an ellipse. Now, in this case, the graph certainly does contain the point plus or minus alpha, comma 0. And you can plug in that alpha for x, 0 for y, and you'll get 1 equals 1. However, the graph of a hyperbola, this hyperbola, does not contain 0 plus or minus beta. Right? To see that, you could plug these values in, 0 in for x, that fraction becomes 0. Plug in beta for y, and you'll get negative 1 equals 1. That's not true, so the point's not on the graph. So to draw a hyperbola, to really understand its shape, we have to calculate these special lines called asymptotes. And an asymptote is like a line that the curve of the graph slowly approaches. To figure out what the asymptotes are, well, we need to try to figure out what the slope of this graph would be, the rise over the run. So we start with this equation, and then we do some algebra. Right? I'm going to go ahead and move the x squared term to the other side, and then multiply both sides by negative 1. That gives us this rewritten expression. Then I'll multiply both sides by beta squared, and then divide both sides by x squared. That brings the equation into this form. and then take the square root of both sides. On the left, we have y squared over x squared, so the square root is just y over x, which looks like a slope calculation. And you have this weird messy thing on the right-hand side. Don't worry about that yet. The key idea is this. As we travel along the graph, as the value of x gets large, well, y is also going to get large. But this ratio, this value of y over x, which is our slope, well, what happens to that? As x gets large, that does not affect the value of the constants, alpha and beta. But as x gets large, see this fraction over here? Right, we're dividing by a very large number. And dividing by a large number makes a fraction very small. As x gets closer to infinity, this fraction becomes 0 and basically drops out. So then what are we left with? Well, the square root of beta squared divided by alpha squared. That's pretty nice because that square root cancels both of these squares. And we're just left with plus or minus beta over alpha. So that's the slope, which I'll write as m, the slope that these curves are tending to. So to draw a pretty decent picture of this hyperbola, we could first, draw our xy axis, and then label the 2 points, plus or minus alpha, 0, that we know are on the graph. Now I also drew in the points 0, plus or minus beta. I drew these in a different color. These are not points on the graph. But once I know this point alpha 0 and the point 0 beta, I can draw a point which is above alpha and across from beta, and then I'll draw a line, a dashed line, passing through that point. That's one of our asymptotes. And we have a line going symmetrically in the opposite direction. Again, you can draw another point here, maybe aligned with alpha on the x-axis and negative beta on the y-axis. And that gives you the other asymptote. Then again, we're just looking for a rough sketch of these curves. We'll start at these 2 points and then draw a curve which gets closer and closer to these green dashed lines. And that's what the hyperbola will look like in this case. Now, that's just a review of conic sections, a trip down memory lane of your earlier mathematics courses. Now, what does this have to do with matrix algebra, which is what we're studying? Well, the idea is we're going to take this more complicated quadratic equation, more complicated because of the xy term, and we're going to write it in a form involving matrices and vectors. So consider this expression. I have a row vector xy, and then I have this 2 by 2 matrix. Notice that I have A and C in this matrix, and instead of using the number B, I use the number B over 2, but I use that twice in these two positions. Now this expression, you could rewrite this as V transpose times A times V, where A is this matrix of numbers and V is the vector of variables, xy. Now what happens when you multiply this out? I can't see a matrix vector product without wanting to do that. If you multiply this matrix times this vector, get A times x plus B over 2 times y. Then on the bottom, we have B over 2 times x plus C times y. Now let's multiply this row times this column. Right? That looks kind of like a dot product. So we'll have x times this top entry plus y times this bottom entry. And when you multiply that out, and I write usually my x followed by y in each case, and then combine like terms, hey, what a coincidence! We got this exact quadratic function that we started with. Well, it's not a coincidence. If you're given a quadratic function in this form, you just take these coefficients and construct this matrix. That will always work. But when we think of this matrix-like function, we call that a quadratic form. It's a little different than our standard matrix multiplications because this vector v appears twice. The function we call the function q sub a, q for quadratic, And the sub A indicates the matrix which appears in the middle here. And on either side, we have the input vector v. It's transposed on the left and as normal on the right. Now the graph that we're interested in, ax squared plus bxy plus cy squared equals 1, that is the set of points which satisfies this equation, which satisfies this quadratic form. QA of v is equal to 1. Or in other words, a point xy is on the graph of this function exactly when QA of xy is equal to 1. And keep this in mind. Now, another fun fact, we've also been studying symmetric matrices recently. And this matrix is symmetric by design. In other words, A transpose is equal to A. If you swap the rows and columns, you get the same matrix. Remember what's special about symmetric matrices. When we diagonalize them, when we write them in the form P times D times P inverse, right, where D is the diagonal matrix of eigenvalues and P is the matrix whose columns are eigenvectors, right? In this case, we can pick the eigenvectors so that P is a rotation matrix. And added bonus, when P is a rotation matrix, the inverse of a rotation matrix is also equal to the transpose of that matrix. Right? So symmetric matrices are great. They're really all about rotations. And what we're going to show in the rest of this video is that the points on the graph of our original function are equal to points on the graph of a different function, a simpler quadratic equation, which has been rotated by the matrix P. All right, so how do we do that? Well, we're going to do just a string of equations. We'll take these through step by step. And this is also going to rely on some of our observations about the transpose. So let's start off with a point, xy, on the graph of QA. Now this means that QA of xy is equal to 1. And if we use the definition of the quadratic form, that means that this matrixy-based equation is true. xy times a times xy is equal to 1. Now let's use the factorization of a and replace a with p times d times p transpose. So that brings us to this equation here. Now this row vector xy, that's the transpose of the column vector xy. And the matrix P, well, I can write that as P transpose transpose, because two transposes cancel out. It seems kind of weird to introduce some complexity, but it's going to simplify out very nicely in a moment. So now, on the left, I've got two transposes next to each other. So I can factor out a transpose here, the catch being, hopefully you remember this, the transpose of a product is the product of the transposes in the reverse order. Right, so I can factor out a transpose up here, then I need to switch the order of these two. And so I get P transpose on the left and the vector xy on the right. And I have to group those in parentheses, but I'd also like to group these two terms in parentheses as well. Notice how we have the same thing appearing twice? P transpose times xy? Interesting. So let's call that W. Let's say W is equal to P transpose times xy. And as we observed before, if we're working with rotation matrices, P transpose is the same thing as P inverse. And it's convenient to switch between these two as necessary. So this long, complicated equation could be written more simply as W transpose times D times W equals 1. But hey, that's just a simple quadratic form there. It looks like now a brand new quadratic form, right? It's got the same format as this, except the matrix in the middle is now D. And it's like we've kind of shifted the P matrices, we've kind of grouped them with W. Yeah, this is the formula for a quadratic form with matrix D applied to the vector W. So in other words, this equation, QD of W equals 1, that means that W is on the graph of QD. And again, this is a different quadratic function that we started with, but it's going to be a little bit simpler, which will be good. Now, what was W again? Oh yes, W was P inverse times XY. So saying W is on the graph of QD means that P inverse XY is on the graph of QD. I really want to take that P inverse and move it from the left to the right. So P inverse times this vector is on the graph exactly when this vector, xy, is an element of P times the graph. In other words, the point xy is on the rotation applied to the graph of QD. Right? And then compare that to our original statement. And that's what we were hoping for. If a point is on the graph of QA, then that same point is on the rotation applied to the graph of QD. So these two graphs are the same. They have the same set of points. Right? The graph of QA is a rotation applied to the graph of QD. Let's soak that in for a moment, and let's go ahead and do an example, right, to kind of make this more concrete. Let's say you want to graph this quadratic equation. X squared plus 10xy plus y squared is equal to 1. Right, we can rewrite this as a quadratic form, and the matrix, right, it's got the coefficient of x squared, the coefficient of y squared, and the coefficient of xy divided in 2, and put it in these two locations. Right, so this equation corresponds to this quadratic form, and it has this matrix, 1, 5, 5, 1. Now we need to find the eigenvalues and eigenvectors. I'm not going to bore you with that entire calculation. We've done that a lot recently. I know you can do it. When you calculate the eigenvalues, this dot, dot, dot means math, math, math. After much mathing, the eigenvalues are 6 and negative 4, which means the diagonal matrix is 6, 0, 0, negative 4. The eigenvectors are 1, 1, or if you want to turn that into a unit vector, divide those by the square root of 2. The second eigenvector, this eigenvalue, is negative 1, 1. And again, you can turn it into a unit vector, dividing by its length. It's negative 1 over rad 2, 1 over rad 2. Might look familiar. Right? That's a rotation matrix we've seen before. So the original quadratic form corresponds to this quadratic equation. X squared plus 10xy plus y squared equals 1. And then, with this matrix D, we have a new quadratic form, QD of xy. That corresponds to 6x squared minus y squared equals 1. And that's awesome. Why is it awesome? Look at this diagonal matrix, right? These zeros right here, that means there is 0 xy term. There is no xy term. We've changed this problem into a simpler problem that we know how to graph. Right? So we take this quadratic equation, right? We turn the x and the y into fractions, doing those substitutions. And so the graph of QA is going to be the graph of QD. We just have to graph this and rotate it by this matrix. Right? Our rotation matrix has this form with the cosines and the sines of the theta. If you solve for theta, you're going to find out it's 45 degrees. All right, so what does the graph of QD look like? Well, it's a hyperbola, right? We know it's a hyperbola because of this negative sign. And because of the values of alpha and beta, right, we can find these 2 points. Again, it's a rough graph. It's a rough graph. It's not to scale. That's okay. So alpha, this distance to here, is 1 over radical 6. And then the distance along this axis, beta, is 1/2. I'm going to draw this point right here, which lies above alpha and across from beta. I'm going to draw these asymptotes. And then, starting at this point I know is on the graph, I'll draw some curves. and the lines approach those asymptotes like so. That's the graph of QD. We have to rotate this to get the graph of QA. And so like so. In this case, the eigenvectors will help you figure out what this angle is. I mean, we know the angle is 45 degrees, but if you didn't know exactly what the angle was, right, you don't have to solve for it exactly. You could just draw this eigenvector. In this case, 1, 1, and then negative 1, 1. Right, so you could draw those eigenvectors. They will line up with the angle that you know. And then along this eigenvector, this is the eigenvector v, I want to move from the origin along the distance alpha. And then I'll draw that point along this line. Then same thing here. I want to draw this point at a distance of 1/2 from the origin. And so this is the rotation of these 2 points. And once again, I'm going to draw these green points right here. And I'll draw negative 1/2. Again, it's definitely not to scale. I'll draw this point down here and over here and over here. I'll draw these asymptotes, these dashed lines. And starting at this point, I want to draw curves which approximate, which move slowly towards those asymptotes. Right? And that's how you draw the rotation of the hyperbola. Right? And that's the graph of the original quadratic equation. Right? One potentially surprising thing is in this original equation, even though all these signs were positive, right, that doesn't force it to be an ellipse here. Right? The fact that we got a negative value in here clued us in that it was going to be a hyperbola. All right, let's do one more example. Right? Let's try to graph this quadratic equation. 3x squared minus 4xy plus 6y squared equals 1. So here's the corresponding quadratic form, the coefficient of x squared and y squared, coefficient of xy, divide it by 2 and put it in those positions. So the matrix for the quadratic form is 3, -2, -2, 6. You find your eigenvalues. They turn out to be 2 and 7. The eigenvectors are 2, 1, and -1, 2. And at this point, we have a diagonal matrix, 2, 7. So we have this quadratic equation, 2x squared plus 7y squared equals 1. Rewrite it in our standard fractional form. That gives us the value of alpha and beta. Right, we know this is going to be an ellipse because we have 2 positive numbers here. And so we get the equation of an ellipse. And to figure out, how the rotation is going to work, right, just in case you don't want to find, or you don't need to find, I'm sure you want to find, but you don't need to find the exact angle. Right, in this case, right, you can take your vector v, your first eigenvector. I'm going to draw it 1/2 and up 1 and draw this point. And then draw a new axis along that eigenvector. Same thing with w, -1 and up 2. And then draw a line through that point. That's our other axis. Since we're working with symmetric matrices, these 2 eigenvectors will always be perpendicular, so that's a nice check. And so these are perpendicular lines, at least I tried to draw them to be. And then you just have to move along, starting from the origin, and you have to draw points at a distance along the new x-axis, this rotated x-axis. Go along a distance of 1/radical 2, and along the new y-axis, that second eigenvector, draw something at 1/radical 7. Okay, you've got your points here, then draw the negations of those points, and then connect them all in an elliptical pattern. And that's what that conic section is going to look like. If you really want to know the exact value of theta, you can totally find that. Right? Take your first eigenvector and normalize it, turn it into a unit vector by dividing by its length. Right? And in this case, this top term will be cosine theta. So you could do cosine inverse of this top value. And then it could be either positive or negative, that value, depending on the sign that you get down here. In this case, this is positive, so we know we're going to take the positive inverse cosine of 2/radical 5. So that's going to be some number. But it's going to look more or less like this. All right, you know I like to say you learn math by doing math. So let's say, just you're given a matrix. And that matrix, it's a nice matrix. It can be factored like so. P times D times P inverse, and some very kind professor has done all the work for you. And here's the diagonalization. So those are your eigenvalues. Look how nice those are. And here's your matrix with eigenvectors. So 3, 1 and negative 1, 3. So the quadratic form QD is going to be this. Look at that. How nice. No square roots. What I'd like you to do is try to draw the quadratic form QA. Now, notice in this case, I haven't actually even given you the formula for the original quadratic form, right? You can actually draw this just based on this knowledge, right? The eigenvectors, those tell you how to draw the rotated axes, and then these values of alpha and beta tell you how far along you have to move along each axis, right, to get your 4 points on your ellipse in this case, because both these are positive. It's interesting, but not relevant. You have enough information to figure out what the original function was. Right? If you're given P and D, you could also calculate P inverse. You could multiply those together to get A, and then you could reconstruct the quadratic form. So if you're interested, this is what it is. When equal to 1, you could also clear denominators to make it look like this. I don't know if it's that interesting. But go ahead, try to draw a good picture. Right? Again, it doesn't have to be perfect, doesn't have to be scale, but just kind of a rough idea of what it looks like will be great. And that's how you use matrix algebra to graph conic sections by way of quadratic forms. Thanks for watching.